Hello everyone, this is Zhibei. Today we will share something about scaling image video data processing by using Ray. Yeah. A quick introduction about myself. My name is Zhibei, currently a member of technical staff at xAI. So my responsibility to building the large-scale image video infrastructure for our Grok multimodal training. Yeah.
Hi everyone. My name is Kai-Hsun Chen. I'm also a member of technical staff at xAI, working in the pre-training team, and currently mainly help them to build a Ray infrastructure, especially for a batch inference, something like that. And I am a maintainer and committer of the KubeRay, Ray, and Apache Submarine. Thanks.
So in this session, we'll cover three parts. First part is about the video curation pipeline for the Grok Imagine. Basically, the video generation and the image generation models at Grok. Another thing is that we will try to address scalability and also the fault tolerance by using Ray Core and Redis Cube. Lastly, Kai-Chen will share how do we auto-scale and address the fault tolerance with KubeRay. So to begin with, let me just do a quick introduction about the Grok Imagine. So Grok Imagine is an AI-powered image and video generation tool developed by xAI. It is both available at the website and also an app. So currently we support lots of features like traditional text to image, image to video, and text to video. For the videos, it also supports audio as well, yeah. So you can download the Grok app and give it a try, yeah. And in the near future, we'll add more features, yeah, like editing, video editing, image editing. Yeah. So here is another example of how do we use Grok Imagine to create some videos, yeah. Okay, now let's talk about some technical details. How do we create this kind of video generation models? So one of the important things is that the data is quite important, yeah. So in my last 2 years, I spent lots of time working with the video data. And before that, people always tell me data is really important for the general models, the foundation models. But at that time, I don't have any ideas. But in the last 2 years, since I built the video generation models, a lot, and then this data is really important. This one is kind of quite true, yeah. So for the data, I think there are 3 key aspects. One thing is about the quality. For video generation or image generation, you need to have a good aesthetic taste. And another thing is about dynamic motions. Without this data, the model cannot learn anything from some static images, yeah. Another thing is about the diversity. So for the video generation models, you need to have a good coverage of the word knowledge. So you need to know how to do some things, play basketball, play soccer. So we need to feed this kind of data for our video generation models. Lastly is about the quantity and the scale. So if you want to have train some pre-training levels models from scratch, you need definitely lots of data. And now let's talk about some basic requirements at xAI. So one thing is about the scalability. So the infrastructure should be able to handle, also can scale horizontally to meet the business needs. So I still remember when I first started this project a couple months ago, my manager told me, if I give you 10x GPUs, can you finish this job in 1 day instead of 10 days? Yeah. So at xAI, we do have tons of GPUs, but the goal is that how do we utilize these GPUs efficiently, and how do you make sure our infrastructure can handle these large-scale jobs? So scalability is really, really important, yeah. And also, just a simple example, double resources means double throughput. 10x resources means 10x throughput. So this is one of the requirements we have here. Another thing is about the low operation cost. Yeah. So the infrastructure should have a really low operation and maintenance cost, because like I build this infrastructure and I will use it. I don't want to build an infrastructure which takes me lots of time to maintain and operate. Yeah, because right now only I was responsible for doing these things. I don't want to spend most of the time to like restart the jobs and then debug what's going on. Yeah. So basically, scalability and low operating cost are the two key like requirements for us when we build in this video infrastructure. Yeah. So this is kind of like a typical video data curation pipelines. The input will be like some videos. And then we will do some like short detections, scene detections. So the video will be cut into several clips. And then we will run some like video encoding algorithms to save the videos with our like FPS, H.264, this kind of like specifics. And then another thing that we will do a dedupe. Yeah. So compared with like other traditional pipelines, we do dedupe really early because we want to make sure like all the videos passed to the next stage are useful for us. So we will get the embeddings from the videos and then search in our like vec database, check if this video is unique. Yeah. After that, we will run some labeling algorithms. So some examples like aesthetics, darkness, motions, OCRs. You can add any kinds of like custom labeling here. So the labeling is really important for the video data curation pipeline. Because like you want to filter out some like good videos data. So you need some like reasonable aesthetic scores. So you can do some filtering. And meanwhile, you can also use this information for the balancing. Yeah. So data mixture is really important for the pre-training level training. Yeah. So you need to make sure like your data has balanced on different aspects. So this information will come from the labeling stage. At the last stage, we will run the captions. So the caption just gives some like a text description about the video. And this will be used for our final video gen model training. Yeah. Now here is like a simple example of how do we calculate aesthetic scores of video. Yeah. So for example, we also have videos, and then we just download these videos from object storage, and then we will run some like decoding algorithm to gather the frames or images from the videos. And then we use some like models like GPU to inference the scores from these frames. And finally, we save this data to our like database. So next, we will talk about like how do we like scale up our current operations. For example, from 1,000 to 1 million or even more. Yeah. So this is our like a diagram. It looks quite simple. Yeah. So one of the philosophy we put in mind is that always don't add complexity. Yeah, just make sure like your system is as simple as possible, because like more components means that your system is like a more we have more like a single point of failures. Yeah. So when I design this system, I want to make sure the system is easy to understand, and meanwhile it's also easy to debug. Yeah. So here we only have like 3 components. On the top is that we have a Redis queue. So Redis queue is used for us to store some metadata. And then we have some like Ray cluster. So this Ray cluster will help us to consume the jobs from the Redis queue. And on the bottom is the Kubernetes clusters here. So basically we build a Ray cluster on top of Kubernetes clusters, and then we define our like business logics in the Ray actors, and then we consume all the data from Redis queue. So in this architecture, we only store the stateful informations in Redis queue. For the Ray actors, we don't store any like stateful informations. And in the later slides, I will explain why we want to do like this. Yeah. Okay, so one of the things that will happen a lot in the large scale system is that fault tolerance. Because if your system is really complex, sometimes one component will fail, which will lead to like a single point of failure. So for example, in our system, there are two single point of failure. One thing is called Redis queue. What if the Redis queue crashed? I mean, the whole system just died because you cannot read any data from the queue. Another thing is about the Ray cluster. What if the Ray cluster crashed? So for example, the Ray head crashed, the Ray driver program crashed. How do we continue? How do we restart? Yeah. So here are some philosophies in our mind. One thing is that we want to make sure the reactor is idempotent. Idempotent means that no matter how many times you try, you always get the same results. This idea is coming from some HTTP API, I think, which is really useful. When you build some distributed system, you want to make sure all of your components can be idempotent, so that you can just restart, you can cache, something like this. So here, we will maintain a reactor pool. So each actor is kind of like a worker. It will just consume our data from the Redis. And then if some actor crashed due to some out-of-memory issues or some other, for example, lost resources, it will be kicked out of our current pool. And meanwhile, some new actor will be automatically started, and then we will put it into the queue. Because each actor is idempotent, so it's fine because they don't have any dependencies with each other. So this is, I think, the key fundamental of our system. Yeah. So reactor is idempotent, and there'll be no relationship, no dependency between each actors. Yeah. Yeah, and then another idea is that, so for example, if some actor crashed, how do we handle these cases? For example, when we process a video data, and then the GPU just have some issues, or we just lost the resources, how do we still keep this failed task? So here we use some classical Redis queue called Redis reliable queue. Basically, we have two queues. One queue is called to-do queue. Another is called a processing queue. So when we first start, we just pick up one items or one videos from the to-do queue. And then the reactor will start processing. If everything is fine, then we'll just push the data to the Redis processing queue. If everything is fine, then once we finish this job, we will just remove it from our processing queue. So this item or this task has been successfully finished, completed. But if during the operations, if this task failed, if this actor crashed, the data will still be stored in the Redis processing queue. And then we can have some other mechanism to push the data from Redis processing queue to the Redis to-do queue. So with this kind of a mechanism, we will never lose any data, even the data if this job failed. Yeah, and then next part, we'll talk about for example, if the Ray cluster crashed, how do we handle these kind of failures? Yeah, Kai-Hsun.
Yeah, thanks, Zhibei. Yeah, and for the next, we will talk about our recently the POC. We want to try to migrate our Ray infra to the KubeRay, and to achieve 3 different goals. The first is to reduce the operational cost. The second is to improve the fault tolerance, and the third one is the support auto-scaling. Yeah, and for the operational cost, the first is that with the Ray cluster CRD, the first is that it will automatically to check the Ray control plane components. On the head part, it will check the GCS, redlat, some agent process, and on the worker part, it will check redlat and agent process status. Yeah, and this allows us to to avoid to monitoring the Ray status manually. And the second one is the observability. The observability is that for a single cluster, we should have an easy way to retrieve the metrics, Kubernetes event, and the log associated with the Ray cluster custom resource. And for the KubeRay side, KubeRay provides the SOI metrics so that we can easily to filter out to retrieve the metrics with the tag of the Ray cluster's DRNN. And for the Ray one is that the KubeRay also provides some path monitor so that it will it has the correct configuration and it has a label you require, and so that you can easily to deploy multiple cluster in a single Kubernetes cluster, and you can view the different Ray cluster status on the single Grafana instance easily. And the second one is the Kubernetes events. Because I think for most of you, when some Kubernetes happen, the first action definitely is like a kube describe the resource. And for the KubeRay, it has a very clear way is that for all the interaction between the operator and the Kubernetes API server, all the interaction has the Kubernetes event. So you can know like which part the communication, all the interaction between the KubeRay and the Kubernetes API server, does it work well or is something wrong happen? And the third one is the structure logging. For the Ray side, like we support the JSON format, and for the KubeRay operator control plane, it also has the JSON format, and each format has a require label, like the Ray cluster CRNAME, something like that. So you can very easily to when you store it into like the CloudWatch or Datadog, you can easily to like filter out based on the Ray cluster CRNAME. So it's pretty easy to associate the log, event, and the metrics with the KubeRay. And the second one is that because in the xAI, almost everything is preemptible. And so you need to make it to be like a fault tolerant. If some cluster crash, something like that, it needs to be able to like restart. And the good thing is that because we try to make the all the stateful information in the Redis queue, so you can see like the Ray cluster is similar to like the stateless runtime, and so in that way we can easily to restart the cluster because to restart the job to resume the job because all the status still stored inside the Redis queue. So and we can rely on the Ray job echo limit to make sure like every cluster always has a running Ray job to constrain the Redis queue, so that we don't need to like manually to operate the Ray cluster. And the third one is the auto scaling. Yeah, there are several levels for auto scaling here. The first one is the Ray application. Like in the Zhibei system, it will auto scale create the different number of the tasks and actors dynamically, and the KubeRay autoscaler support like to spin up a new Ray pod to allocate to schedule this new Ray task and actor. So this is the current scope, and something we may do in the future is to like spin up new Ray cluster custom resource across the different Kubernetes cluster. Yeah, because we have a multiple Kubernetes cluster in our infrastructure. Yeah, and these are 3 points that we currently POC with the KubeRay, and we got some promising result. And we will migrate to the KubeRay to deploy our Ray cluster recently. Yeah, and the last thing is like maybe the most important thing is that we are actively hiring, and this is our primary goal here. So please send your CV and information to like our emails, and we will stay here. So feel free to reach out. Cool. Any questions?
Bay and Kai-Hsun, some question, please raise your hands.
I had a quick question. I'm familiar with the kind of data deduplication for text, but I'm not so familiar for video. Is there a substantial kind of portion to this about how you dedupe video that's different from the text chain, or is it very similar?
Yeah, I think one of the difference between text and video is that video takes more operation, more like computation cost. Yeah, for example, even like a simple video decoding and encoding takes lots of time. It's like CPU intensive, and also lots of like video operation. You need it's basically like computer vision. You need lots of GPUs. Yeah, this is one thing. Another thing is about the storage. Yeah, video is much more like much larger than the text, so you need lots of storage. And another thing like also coming with the storage is that the bandwidth. So when you want to process large-scale videos, right, you need to make sure your network is never the bottleneck. Yeah. So basically these things. Yeah.
So I have two questions. First is that in terms of fault tolerance, if you have a read job, so if the read cluster, the head node dies, and then it automatically restarts. And then if the read job is marked as failed after a while, when the head pod restart, is it that the read job just has to be failed and retry?
Yeah, so what's your question?
So my question is, if the head pod dies, is there any way that that read job can be resumed, or the read job just has to?
Oh, yeah. I got to a point. I think the main thing here is that if a driver process is on the head pod, if it crash, the job will fail. I think one like the special case is the detach actor. Yeah, but we don't use a detach actor. Detach actor is a special actor which is decoupled lifecycle with the driver process. But our way to do that is that we don't care about the job fail or not, because all the status is stored inside Redis queue. So you can see like our Ray worker is the status. So we just resume it, and the old operation is idempotent. So we can. It doesn't matter how many times we process a single like a video, because it will generate the same result. So we just promise at least once semantic. So this is how do we achieve fault tolerance. The job will die in the Ray. This is a Ray limitation.
So you mean in the middle of the video processing, it will die, so you just reprocess that video?
A second?
You just process that video again?
Yeah, because I think as the Zhibei slide shows, we have a, where's the queue?
Yeah, this one.
This one? Yeah, we have a queue, and the Redis provides atomic operation to like pop from a queue and push to a queue. This is atomic. So that we can ensure like if it doesn't be done, we will always process at most once.
Okay, thank you.
Not at most one, at least once.
There's a lot of questions. I see a lot of questions, so maybe everyone can make a line here that I can pass it through. Thank you.
Hi, you talked about how to handle the Redis queue death. So how did you handle that?
You mean how do we handle the Redis fault tolerance?
Yeah.
Oh yeah, I think there are like a couple ways. Like one thing is the Redis like replications. You have lots of copies, and also I think Redis Enterprise, they also provide some like mature solutions like Redis clusters, which can make sure. Yeah, and also I think one of the common ways that you definitely need some like persistent storage. So when you start the Redis pod, you need to make sure like all the data are stored in local or some places. So when the Redis pod crash, it can still read the data back. Yeah.
Hey, Kai-Hsun, awesome information. Thank you for sharing. So you alluded to multi-cluster being on the near-term roadmap. Ann Holler published a series of blogs yesterday about multi-cluster stretched clusters for placement and scaling and doing configure and upgrades. So I'm curious about your thoughts, both of your thoughts on what do you think about a stretched Ray cluster spanning across multiple Kubernetes clusters?
Oh, you say for a single Ray cluster?
Correct, yeah.
I think for me is that my experience like, I think for a short term I will not try to do that, because this means that because if it's across like a different region, I have some experience about that. The network is much more unstable, and so it means like you need to rely on the Ray internal, like retry something like that. I think we do a lot of improvements. And I also did a lot of improvement in the N-scale before. Yeah, but I think for me, I will still make the Ray status for now.
Okay, so standalone Ray clusters across a fleet of clusters, right?
Yeah.
Thank you.
Oh, hi. So thanks for sharing this. I have two questions. First one, so I see in the descriptions you mentioned your system can scale up linearly. So I was wondering how you achieve that, especially for the video decoding. And the second question is, I'm not sure if this is convenient for you to answer. I was wondering what library you use for the video decoding. Are you using Torch Vision or any other libraries? Yeah, thank you.
Okay, yeah, so first about the horizontal scaling, right? I think we have two levels of scaling. First level is about inside the Ray clusters. We can add like, new reactors which can process. And another layer is called the cluster level. For example, because xAI has lots of data centers, and if we want to utilize all the GPUs across different data centers, normally we'll just start like different Ray clusters, in different data centers. So this is another kind of like horizontal scaling, yeah.
Yeah, but I was wondering the scaling ability is like, see, when you add more reactors and or you add more the reclusters, what's the performance of this system? So will your performance also be scaled up, like see 2 times or 8 times?
Yeah. That's a really good question, yeah. I think this is also the key, fundamental requirements for us. Like we want to make sure the system can horizontally scale up. And according to our experience, I think like a single Ray cluster can handle, for example, 10,000, 20,000 actors. This is kind of like I will not say the maximum, but kind of like the comfortable actors numbers. Yeah, but we haven't tried like 100,000 actors like in a single Ray cluster. So in this case, we'll probably like spin up a new Ray cluster to handle it, yeah. In this case, I think the data processing will definitely scale horizontally. But another thing is that when you scale by your jobs, sometimes it's not a bottleneck maybe by Ray, maybe bottleneck by other stuff like the bandwidth.
Communication.
Yeah, so you need to figure out like what's your bottleneck and address the bottlenecks, yeah. So ideally it can scale up like horizontally, yes.
Okay, cool. So can you answer my second question about the video decoding? Which library you are using, or so is that convenient for you?
Yeah. I think video decoding is a really common problem. I think there are three things that we are using. The one is like FMPEG, traditional FMPEG, and another library we are using is called Decode, DECORD. It's also really old, but I think it's quite a convenient library. Another thing is called Torch codec. Yeah, there are three. Yeah.
Okay, cool. Thank you.
Hi, so I have one question. So given that you have the Redis queue and you are using the 2-queue mechanism, why are you using reactors? Like, why not just pods in Kubernetes and Kubernetes autoscaler?
So your question is that why do we use the reactor instead of the pure Kubernetes?
Or job, yeah, Kubernetes job.
Yeah, I think one good thing for us is that Ray is like a glue like the cluster level and the application level together. For example, like in the Kubernetes part, it will horizontal scale based on like your metrics, your physical utilization. But for Ray is that I can specify like this task actor require how many resources, and each can trigger the scale up. So you can see like it's like we can spend like a much less effort to glue the application and the cluster together. Yeah, I think this is the main reason. And the Ray is it is like a single controller stuff, and it makes us much easier to architect, and we can do some like a fault tolerance retry, something like much easier.
Yeah, another thing I want to add is that like a reactor, you can simply specify some like number of CPUs, number of GPUs. For example, for some small models, you just need like 0.1 or 0.2 like GPU. I think which is quite flexible for us to use, yeah, compared with like using Kubernetes pods directly, yeah.
I had one question on your state itself that you store in Redis. So how do you also assign the data paths itself to actors? Is that predetermined, or do you do it on the fly? And in addition to this path itself, what else do you store in the state?
So you mean like how do we assign tasks to different actor, right? Yeah, that's a good question. So for each actors, like we will have like specified which queue it will consume. So when we start these actors, it will automatically like consume the item from this queue, yeah. So there's a parameter that we will just give to this actor. Yeah.
Hi, I was trying to understand what the Ray actor is doing exactly, because you have a multi-stage pipeline, right, that does like decoding, deduping. So for a given Ray actor, is it running these steps sequentially for one video?
Yeah, that's a really, really good question. I think for our use case, for each job reactor, we only do one thing. Yeah, for example, we only do like a short bond detection. We only do like video encoding. So we never like put like lots of like operations like in single reactor. Yeah. So this is the one thing that we want to make sure that the system is like lightweight, but it can hold on scale up. Yeah.
All right, thank you so much. Another round of applause for the speakers. Thank you.